Okay, hi everyone. I'd like to welcome you to the fourth episode of this third season of the Young Researchers Forum on Detonations. I'll introduce today's speaker, Vianney Monnier. Vianney holds a master's degree in engineering from l'École nationale supérieure des arts et métiers, ENSMA in France, and a master's in thermal power from Cranfield University in the UK in 2020. He's currently in his last year of his PhD at l'École nationale supérieure de mécanique et aérotechnique, or ISAE-ENSMA in France, and he's supported by a grant from the French Ministry on Higher Education, Research and Innovation. And he's under the supervision of Doctors Vidal, Rodriguez, and Zitoin. Today, he's going to be talking about his experimental and modeling work that addresses detonation structure and dynamics. And he'll be showing an emphasis on the three-dimensional properties. So just to let everyone know, we're going to record the session and we'll be putting it up on YouTube. And you can also access all the previous talks on our website, which I'll post in the chat in a second. Also, if you have any questions during the talk, please post them in the chat, and we'll have our discussion session at the end, and you can either, again, post your questions in the chat or speak up directly. So without any further ado, Vianney, thank you very much for showing up. It's a pleasure to have you with us, and I'll let you share your screen now.
Thank you very much, Shen. All right. So, okay, you should be able to see my presentation.
Yes, I am.
All right. Okay. Well, then, first I will recall some notions about detonation instability. Then I will assess the steady detonation propagation in smooth tubes. Next, we will see some work about the detonation propagation through an orifice to finally conclude with the ongoing work here in Pprime. So reaction zones in detonations are unstable and therefore they have a cellular structure. The pattern and the size of the structures are a result from the interplay of chemical kinetics and the tube geometry. For example, on these two recordings, the mixture, the initial pressure, and the cross-section area are the same, but they have different frontal and longitudinal recordings. So this work addresses the influence of tube geometry in multicellular detonations. Two lengths can be used to quantify the instability of the detonation. Our first quantifier would be the hydrodynamic thickness, first introduced by Solukin, and it was further investigated by Lee and Radulescu. It's the effective length of the reaction zone, and it's much greater than the Zeldovich von Neumann-Doring total reaction length. But another quantifier, which is commonly used, is lambda, the cell average width, which was first identified by Denisov and Trochin. It is calculated from measurements on longitudinal soot recordings. And in some mixture, the standard deviation of the cell width is negligible when you compare it to the average cell width. But in others, it is of the same order. And for those mixtures, the representativeness of the average width is quite questionable. Because indeed, the cellular structures can be categorized from very regular to very irregular. For example, if you mix hydrogen with oxygen and you dilute it with argon, you will end up after detonation with a regular structure. But if you detonate hydrocarbons that are mixed with air, you will end up with an irregular structure. So to date, the interpretations and the models for the cell regularity are mostly based on chemical kinetics. The latest contribution for that being the key number, where the higher the kin number, the more irregular will be the mixture. So regularity is based mostly on longitudinal recordings, but as we saw earlier, we know that detonation cells are three-dimensional. And this is why we're going to use the soot plate technique for both longitudinal and wall recordings. And that way we're going to characterize the detonation three-dimensional structure. We will have information about from views. The tubes we're going to use are round and square. Two of them will be of equal cross-section area, that is 16 centimeters squared. And we use the stable hydrogen-oxygen mixture, stoichiometric, and we're going to dilute it in 40% of volume of argon, because it is reputed for its regularity, so it will be convenient for us to compare from one tube to another. And so for completeness, we also investigate greater cross-sections for the round and square tubes. The experimental apparatus is very classical. We ignited the premixed gases using either a spark plug or an exploding wire, and we reduced the DDT distance with a 1 meter long Shellkin spiral. Now, to have a relevant recording, we need to ensure that the detonation is steady before entering the soot foil section. And to ensure its steadiness, we use pressure transducers to check that the velocity is constant, and we make sure that the average cell length is constant throughout the longitudinal soot foil. Here are some results that we obtained for different initial pressures. So at the top, you have the front view recordings with the corresponding longitudinal ones for the different initial pressures. At the lower initial pressures, we can identify the long time observed arrangement of squares and rectangles on the front view of the square tube. But in contrast, it's quite irregular in the round tube. Also, if you look only at the longitudinal soot foils, you can identify the transverse waves that travel perpendicular to the soot foil on the square tube. When you increase the initial pressure, the arrangement of squares and rectangles is locally deformed, but you can still identify the set of transverse waves that travel perpendicular to a soot foil in that case. But if we increase even further the initial pressure, we eventually end up with a fully irregular structure on the front views of the soot recordings. And we cannot see the transverse waves that travel perpendicular to the soot foil anymore. However, it is irregular on the front views, but it is still very regular on the longitudinal recordings. Looking at only a blow up of the recording, we cannot tell which tube it comes from, because the recordings are irregular and quite of the same size. They are independent of the tube cross-section shape, but cross-section area as well. This graph plots the cell average width against the initial pressure. We measured it from more than 50 values of cellular cell width on the longitudinal soot prints. In red are the values from the tubes with the same cross-section area, and in blue the ones from the greater areas. The crosses are the data by Strello and Bartel, available on the Detonation database. So what this graph shows is that when we decrease the initial pressure, the values from one tube to another will tend to diverge, despite having the same cross-section area. So that means the influence of a tube increases not only because of the dimensions, because they are the same for the red values, but because of their shape. Conversely, there is a limiting initial pressure where the values will converge, and this is consistent with the front views becoming regular, whatever the tube. We identify, in this case, this limiting initial pressure to be around 60 kilopascals, but we can assume that this limit is very specific to the 16 centimeter squared cross-section area. We can assume that this limit is a function of the tube itself. Now, our work points out that irregularity is the rule for front view recordings, and that means that regular front views is for marginal multicellular detonations. So in that case, in the case of irregular front views, can we define a relevant average cell width, which will be independent of tube geometry? Well, to do this, we're going to use planar graph theory, and then we will couple this with geometric probabilities and the ZND model. So first, we need to describe the front view recordings using the semantic field of planar graph theory. The transverse waves become the edges on a graph, and if we use the Euler-Poincaré formula, we obtain the average number of cells, the average number of edges per face, or if you prefer, the average number of transverse waves that bind each cell. Now, physically, the field of material velocities must match behind the transverse diverging shocks. So that means we have a very little number of vertices that are shared by more than 3 edges compared to unity. So the average number of edges per face is 6. That means that the time average frontal tessellation for the front view recordings is a set of hexagons. Experimentally, that means we can obtain the cell average width from the number of cells that we count on the front view recordings. But you would expect to count hundreds of them, and this introduces an interesting uncertainty of around 30%, because it corresponds to the orientation of the cells with respect to the soot plates. Now, the basic assumption is that the cellular and the ZND processes must burn the fresh mixture at the same mass rate for sufficiently large periods of time. Then, from high-speed recordings, we know that the combustion is done behind the transverse and the higher velocity waves, which means at a much faster rate than the cellular one. And if we couple that with the Chapman-Jouguet velocity, we obtain a first expression for the length cell, the cell length, sorry. And if we use mass conservation, we obtain another expression for the cell length. Both of them are dependent on Y. Y is the mean mass burned fraction. And to obtain Y, we use the stochasticity of the front view recording. So the stochasticity expresses that the successive front view patterns during the same experiment is statistically equivalent to the patterns from one experiment to another at the same front position. So combustion efficiency and the transverse waves position behave like segments that are randomly dropped on the average tessellation. As we saw earlier, that average is a set of hexagons. So this is equivalent to a Buffon's needle problem, which we apply to hexagons, and we obtain that way Y. Then we post-process the ZND profiles, and we obtain the cell length, which is proportional. It's linked by geometry to the cell mean width. So here's some comparison between the calculated values using Konov's detailed chemical kinetics and experimental data available on the database. Overall, for the different mixtures we tested, and if we use the adapted chemical schemes, we obtained the right trends and the right order of magnitudes. We are well within the accepted experimental uncertainties, and we need to keep in mind that our model only applies when the number of cells is high enough. So the characteristic time is much less than the acoustic time of the tube. We wanted to translate this limitation as a criteria between the cell dimension and the dimension of the tube. And our calculations match much better with experimental data, where it's safer to say that the tube has no influence on the cell size. Now, that concludes the part about the characterization of the three-dimensional structure for steady detonation propagating in smooth tubes. Because we have limited time together, I cannot go deeper into details, but if you want, there are some related publications, and hopefully I will present the model during next ICDERS. And now that we characterize the steady detonation in smooth tubes for the different cross-section areas, but the same, not the different cross-section areas, but different cross-section shapes, the areas are the same. Let's see what happened when we put an obstacle during the propagation. For example, on those two soot recordings, the conditions for the obstacle, the mixture are the same, but the detonation has quenched in both tubes, but only reignited in the square tube. So we will see that the cross-section shape has a strong influence on the detonation behavior behind the obstacle, and that has strong consequences on the safety for industrial infrastructures. For the phenomena of detonation initiation, or in that case, reinitiation, it is governed by the Soisson mechanism. If you have a gradient of induction time, temperature, or pressure, you can have flame ignition, and those flames will create compression waves that can amplify. And if there is a coherence between the flame ignition and the energy release, the compression waves will amplify to a point where they are strong enough to ignite the mixture. And a compression wave that ignites a mixture, that is a detonation onset. So there has been extensive work on this topic. There's an extensive review by Sicarelli and Dorothy. I would recommend that because it's quite extensive. It sums up the work that has been carried out yet, because many variables have been investigated to date: the shape, spacing, blockage ratio, size, thickness, and number of holes, for example. But there are no systematic comparison between the shape of the channels, between round and square cross sections. Plus, the detonation average cells intervenes in criteria for detonation onsets with obstacles, and as we just saw, this average cell can be influenced by the tube itself. So the experimental apparatus is basically the same. We just replaced one of the pressure transducers with a 5 mm thick orifice plate. And at the end of the tubes, we placed a ball of iron wool. That way we prevented reignition from end wall reflections. In the square tube, we could replace the sooted plates with quartz windows. That way we could enable shadow graph imaging. And first, we will use this shadow graph to identify the different behaviors downstream of the obstacle. And then we will compare them with what we see in the round tube, because in the round tube, we can only use the soot foil technique. So I'm going to show you some shadow graph and we will comment afterwards. Do you see the video moving? Because we had some trouble yesterday.
Yeah, I can see it.
All right. Okay, so in that case, what we see is a failed reignition because there is no detonation downstream of the obstacle. So first, what happens is that we see a complex shock wave and a complex made of shock and combustion waves that pass throughout the obstacle. And when during the diffraction of the shock wave, there is a decoupling with the combustion front. And then the diffracted shocks reflect on the four edges of the square tube. So in dashed are the ones that reflected on the quartz windows. And then those four reflected shocks recombine together to create a planar shock wave. But let's see what happens if we further increase the initial pressure and we change the mixture as well. So the complex combustion wave, shock wave decouple, but when the reflected shocks refocus together, they are strong enough to ignite a detonation. So here you have the cellular structure on the longitudinal soot plate before the obstacle and downstream of the obstacle. And as you can see, the cellular structure is longitudinally more irregular after shock onset than upstream of the obstacle. Let's increase even further the initial pressure and reduce the argon dilution. So in that case, the max stems that are produced during the reflection of the shock converge, they sweep along the walls, and when they meet each other at the corners, they are strong enough to ignite, and you end up with four overdriven detonations that eventually recombine and relax into the steady detonation. And you can see that here and there on that foil. You can see two of them, and you have to keep in mind that it happens at the same time at all four corners. We can sometimes observe both corner onset and shock onsets. But what you see is that on the soot recording especially, you can see that there is an appearance of the cellular structure, but it fails, and then again there is a shock onset, which is slightly overdriven in that case. Finally, if we even further increase the initial pressure, the diffracted shock is strong enough to ignite the mixture when it reflects on the wall. And what you end up is either a detonation or a deflagration. So in that case, on the shadow graph, it's quite difficult to see the shock wall onset because it's a deflagration, as you can see here on the soot foil. And after that shock wall onset, you see the corner onset, which is a detonation there. This is chemiluminescence, which is corresponding, and you see that it's much more luminous after the onset in the corners. But eventually, if the initial pressure is large enough, it can fully ignite the detonation. Now, let's see what happens in the round tube. We can only use the soot foil technique, but now we identified what happens in the square tube, so let's compare. This is what a failed detonation reinitiation looks like, with in yellow the imprints of the shocks that periodically imprint on the soot foils. We can also observe DDTs with run-up distances that are much greater than in the square tube because there are no corners. We can also observe shock-shock reflections with shocks before imprinting and then a detonation. And finally, we can observe shock wall onsets. Overall, all things being equal, and I mean by all things, the argon dilution, blockage ratio, and initial pressures, the limits for detonation reinitiation are more constraining in the round tube, which is good news if you mean if the obstacle is meant to be a detonation arrestor in industrial infrastructures. However, we see that the different behaviors from one tube to another are observed on ranges of initial pressures where the tube has an influence on the steady detonation itself. Now, we showed that there is an influence of the cross-section shape on the steady detonation propagation. We can move away from that influence by increasing the initial pressure, or that is, increasing the number of cells. And for that case, we propose a readily implementable prediction model for the cell size, which is based on graph theory and geometrical probabilities. And we also investigate how the tube cross-section shape influence the transient phenomena. Overall, it is easier to reinitiate into a square tube than into a round one. But is that because of the cross-section shapes have an influence on the mere steady detonation, steady propagation? Or maybe if we move away from that range of initial pressures, we will observe exactly the same. So we need to, we are currently working on that question. And finally, since the average cell width can be influenced by the tube itself, can we find a common criteria based on that quantifier for all the tubes? We are currently working on that as well. Before taking questions, I would like to thank the organizing committee for this, for the initiative of this forum. Shem, I will give you back the control of the presentation.
Yeah, thank you very much. That's very, very interesting. I mean, these are beautiful photographs of soot foils. So I congratulate you on the amount of effort that it must have taken to get those experiments done and do them very nicely. I'll take any questions from the audience. If you want to write them in the chat or speak up or raise your hand, I invite you to do so right now. And while you get that down, I'm gonna ask you a question that I had on something you said. You said that the characteristic time is much larger than the acoustic time of the tube, and then you have a decoupling between the regularity or the shape of the cells and the tube. And I was wondering if that characteristic time corresponds closer to the induction or ZND time, or more to a cell or to multiple cells, and what you found there.
I believe it's a question of characteristic time of a cell, because each cell is confined between other cells. So each cell confined the others, and that way we are away from the solid walls that can interfere with that. That's what I meant by this ratio of characteristic times.
Yeah, I mean, I think it's interesting because, you started off your presentation mentioning, we've got the hydrodynamic length, which is maybe 3 cells long, and then you've got length scales that are all the way there. And yeah, that's where I was going with that.
Okay.
Another question I have is, do you see, I mean, you worked with pretty regular mixtures, but do you see multiple scales appear on any of your soot foil? Like you have big cells and you have small cells within them.
Not on the mixtures we use. For the stoichiometric H2O2 heavily diluted in argon, you can see, well, I can show you the I can show you again the soot foils we obtain. So, for example, that's, well, let's see, for the steady propagation. Over there, yeah, you can see that there are no cells within bigger cells. Maybe that's because they are too small, but I don't believe so. And for the undiluted mixture, you can see that there are as well no. I just need, yeah, that's argon diluted, but that's undiluted argon. So we can sometimes believe that this is a bigger cell which contains all the cells, but that's just the transverse waves that travel perpendicular to the soot foil. So no, we don't observe double structures for those mixtures, that is. Yeah,
I was wondering maybe if you had done some other mixtures, but yeah, this is super interesting.
Maybe we need to do more experiments with other mixtures.
You got a lot on your hands already. I'll invite any questions from the audience. Does anybody have something they'd like to ask? Patrick Meager, you have your hand up.
Yeah, thank you. I had a question. Well, yeah, I had maybe 2 kind of related questions. So in the first, I think it was slide 10, you show the cell size as a function of initial pressure for the 2 different tube geometries. Did you record a average wave speed at the same time? Or do you have any guess as to what the average wave speed looks like?
Yeah, so we did record the average wave speed to ensure that it is steady. However, there are some, it's quite difficult to measure precisely the average wave speed because if you have cells that are, as we use pressure transducers, they have an area of around a few millimeters square. Mm-hmm. So if you have big cells compared to the transducer itself, that can be a problem to measure. The average velocity is quite different from the local velocity on the scale of the cell. Yeah.
Okay. So I guess to maybe press you a little bit, does the round tube seem to have a slower global wave speed than the square tube, or no?
Yeah, I don't have the numbers around here, but yeah, this is something that we need also to assess. Yeah.
Yeah, I'm just curious. And then my second question is, if I understood the graph theory correctly, you have to assume a wave speed in there, correct?
Sorry, I didn't hear you.
If I understand the graph theory correctly, you have to assign some average wave speed, correct? Like the CJ speed, or no?
Oh, yeah, we for on the scale of the cell, we do have.
So if you were to reduce that by 10%, you end up with a larger cell?
Sorry, what?
If you were to reduce the CJ speed, introduce some velocity deficit, does the graph theory tell you you need a larger cell then? Or come up with a larger cell size?
Oh, the velocity of the cell doesn't intervene into the graph theory part, nor
Okay,
the
thank you.
fancy needle problem. It will only intervene into that relationship, but in the end, since we are working with averages, both in terms of statistical on the same experiment, but also time average. That's how we manage to that's how we use the detonation velocity.
Perfect, thank you.
Okay, we have a question from Matej Radulescu.
Yeah, thanks very much for the great talk. I have two questions. One is a question and one is a comment. The question is, have you tried doing any sort of like correlation on your patterns of your frontal cells to see whether there's like some intrinsic correlation length in terms of like sizes of these cells or anything of that sort?
We did try, however, as you can see, on the front view cells, it's quite hard to post-process them and to end up with a distribution of sizes on the front view, because, as I said, you need to have a large number of cells on the detonation front, and that means because of our experimental apparatus, they are really tiny and they are too tiny to be detected, to be sometimes differentiated from one another. So it's quite hard to post-process the soot foil that we obtain, but hopefully we will find some code which is able to post-process that and to get a distribution of sizes and shapes as well. That will be interesting.
Yeah, I think that would be very interesting.
Mm-hmm.
My second question is more of a long term, I guess. In your current investigation, you weigh every track the same, right? So if you see a track, it's a track, but there's no information on magnitude or strength or something related to the strength of that feature that is recorded. Although you do see some weak tracks and some strong tracks. So have you tried or have you thought about like how we could go beyond just measuring distances between tracks and somehow experimentally probe like the strength of the features? For example, if it's a track, then it's maybe like some sort of like vortex sheet that rearranges the soot to quantitatively extract more information about the strength of the track.
I believe that that has been done using not at Pprime, but using paper that is sensitive to pressures, and they wanted to quantify those tracks to relate those tracks with the local pressure, and their idea was that it was due to shear stress, but they could not match exactly between their calculations and what they measured. That would be interesting to see what happens on the, maybe by combining shadow graph imaging and soot foil technique at the same time to see how all the tracks are drawn on the, yes, that would be quite interesting.
Thanks.
But unfortunately, we could not do that yet.
Thanks.
Okay, our next question comes from Jackson Crane.
Hey, thanks. Yeah, so this is really nice work. Thank you very much. Our collaborators and us at the University of Duisburg-Essen performed some simulations that are very similar to the experiments that you did. Namely, we did large 3D simulations. This case, they're hydrogen, oxygen, no argon, and they're in square channels and round tubes. And so one of the things that we found, first of all, we see very similar results to your small channel. We couldn't do these massive simulations that you have experimental results for that show the convergence of the two behaviors, but we see the bifurcation of the behaviors in the smaller round tubes and square channels. So really good agreement between the two. And one of the things that the simulations allow is actual examination of the thermodynamic states inherent to these different detonations. And we find that the square channels actually have pressures substantially higher than that of the round tubes. When you see this highly aligned structure, basically you have called triple lines that intersect in 4 different places that lead to extremely high pressures in excess of what you see in the round tube. And I'm wondering if you have any thoughts about the role of the thermodynamic state in the detonation versus the geometry when reinitiating. So when you go through an orifice plate, if you have a stronger phenomena incident on the orifice plate, maybe that is one of the factors that leads to a more robust reinitiation phenomena as compared to just a geometric constraint.
Well, yes, in the square tube, it tends to reignite easier. And I do believe this is because of the, for example, in the corner offset onsets, this is definitely because of the Mach stems that propagate along that sweep along the tubes. And when they meet another Mach stem at the corner, they produce a very strong detonation. But in a round tube, you have no corners, right? So that wouldn't happen. And there was some work here in Pprime about detonation, deflagration to detonation transitions in squared channels. And they saw that statistically, it also happens in the corners more than anywhere else in the cross-section. So that would be interesting also to investigate other shapes of tubes, but that would be quite expensive in terms of time and apparatus. But yeah, I do believe that the thermodynamic states are influenced themselves by the shapes of the tubes because of the way the waves travel along those cross sections.
Yeah, I mean, you could potentially isolate it by having a square channel with an orifice plate followed by a round tube after the orifice plate, right? To see if the incident cellular structure actually affects the reinitiation. Probably it's a second order effect if I were to guess, but I was just curious. Thanks.
That's a good question. Yeah, that's something that would be interesting to try.
Thank you very much. Are there any other questions from the audience? Otherwise, Vianney, thank you very much for your presentation, and I look forward to seeing your presentation at ICTRS also this summer. So yeah, thank you for coming. We'll have another presentation again next week. Are there any other comments or perhaps messages from my co-hosts?
Yes, I actually just today I received the abstract from Pierre Carlo. His presentation is going to be next Friday. Yeah, let me check the time. I don't want to give you wrong information. 1 second. So yeah, the time would be next Friday, February 24th in Central European time from 4 p.m. to 5 p.m. So that's yeah, you can do the conversion to the North American time and the Eastern Asian time.
We will be sending out emails and putting it on the website too.
Preparing the flyers and put the information on our website and sending out the email to our mailing list. So for those who are attending these webinars, if you are not yet on our mailing list, please let us know and reach out to one of our organizers. Then we will add you to the mailing list, and I will keep posting the information on LinkedIn. Then I guess some of you also see the information from there. Yeah. Great. Thank you, Vianney, for your excellent talk, and hopefully to see you later this summer or in France for this European combustion meeting. Yeah. Great.
Okay, we'll
Thank
see
you.
everyone next week. Thank you very much.